Hello and welcome. This is the introduction to Chapter 4. So Chapter 4 is on reactions in aqueous solutions. So the topics in this chapter include discussion of the general properties of aqueous solutions. That just means that these are solutions involving water. So anything aqueous is something dissolved in water. We'll talk about precipitation reactions. This is where maybe you start with two water-soluble substances. So let's say we have an AB. We might write AQ. That kind of tells us that this thing's dissolved in water. We'll react that with CD, also dissolved in water. That maybe will make something like an AD, where we get a solid, and then BC will be paired up as, we might actually call it CB, even though we'll go through what this might mean later, but like a CB where that remains dissolved in solution. So you start with like two liquids, mix them together, and then you end up forming a solid as they mix together. That's what a precipitation reaction is. We'll talk about acids and bases and talk about neutralization reactions. Acids and bases react together to form a salt and water. So acids and bases react together, and we'll talk about some of the products of those reactions and how to write those reactions and balance them out and understand them a bit more as we go along. We'll talk about oxidation reduction reactions. These are reactions where maybe you start with something uncharged like sodium and chlorine in their elemental form. So imagine taking sodium, metal, chlorine gas, react them together to form NaCl. Solid, this is one of those combination reactions out of chapter 3. And so if we have this combination reaction taking place, we're actually developing charge here. So we're changing the charge states of the elements. And so we have sodium losing electrons, chlorine's picking up electrons, gaining them. So oxidation is the loss of electrons. Reduction is the gaining of electrons. You might remember Leo the Lion goes grr. Some people remember oil rig, where oxidation is loss of electrons, and then reduction is gaining electrons. So you might remember a few different slangs for understanding that in this particular reaction, sodium is undergoing an oxidation. It's losing electrons, so it's oxidized. Chlorine's picking up the electrons, so it's gaining electrons, and the chlorine atom is reduced in that particular reaction. But we'll go through classifying things like oxidation numbers and then determining which elements are oxidized or reduced in a reaction, and then perhaps maybe predicting a few of these reactions as well. Finally, we'll talk about concentrations of solutions. So this will be like the moles of a solute dissolved in the volume of solution. And so this will be our molarity unit. So molarity is just moles of some solute divided by volume of solution. Our main unit here is moles per liter. It's the liter of the entire solution, and not necessarily just the pure solvent. So of course, you have the idea that you have a solute dissolved in a solvent. In that case, this chapter is water. And then you can describe the solution that results from the dissolving of that solute in the solution. So finally, we can do solution stoichiometry problems and do some chemical analysis as we wrap the chapter up. This will be doing problems where, like if you take Na, say OH, and react that with HCl. So just do kind of a classic acid-base reaction. Let's imagine we're producing NaCl and water. That you can imagine if I told you how many grams you have of HCl versus a number of grams of NaOH, and this is like a chapter 3 problem. You'd be figuring out excess versus limiting reactant. Well, here in this chapter, instead of giving you grams and molar masses for substances that are more commonly dissolved in water, we'll tell you more like the molarity of the solution of HCl versus NaOH and ask you maybe how much product gets formed or how much of the two reactants are needed to react together. So we'll be introducing the idea of taking the number of liters of a substance times its molarity. This will give us moles. So if you take the molarity, moles per liter, times the volume of solution, that gives you the moles of the solute in the solution. So we'll be, solving these problems using many of the ideas out of chapter 3 that we learned last chapter, but we'll just be applying this new unit of molarity through the solving of those particular problems. Let's take a quick look at solutions. So the idea of a solution is we have two or more pure substances mixed together. But in the case where we have a solvent, where we have a liquid phase, then we start to think of these as being like an aqueous solution when water is the particular solvent. So if water is our solvent, then the term we give that type of solution is an aqueous solution. So you can dissolve or mix, probably mix is a better word for methanol with water, because it turns out that they're completely miscible with each other. So when we have two liquids, like methanol exists naturally at room temperature as a liquid, water is a liquid. So whenever two substances are liquids, the question is, are they miscible with each other, where they mix completely in any proportion? So we can put a little bit of methanol and it mixes perfectly with water, and we put a little bit of water and methanol and they mix perfectly as well. And really what we're doing is the molecules still exist as they normally do, they just interdisperse amongst each other in a random homogeneous fashion. So it just forms a simple homogeneous mixture where we still have our separated molecules, no reactions really taking place. In the case of methanol dissolved in water, we just have methanol and water molecules intermixed together. So something happens though when an ionic substance dissolves in water. If an ionic substance dissolves in water, you have all these, actually the greens are the chlorines here, but the green chlorines have a negative charge, the purple sodiums have a positive charge. You have all these electrostatic forces of attraction holding the ions together. That's why sodium chloride has such a high melting point and boiling point. If you look at NaCl, exists at room temperature as a solid, melting point's about 800 degrees C. Compare that to HCl. I don't know its melting point, I'm just kind of bringing this example up, but it's a gas at room temperature. Its melting point and boiling point are going to be well below room temperature. That's why it's a gas at room temperature, not a solid or a liquid. And so the forces that hold HCl molecules together are not nearly as strong as those that hold NaCl together. But if you dissolve some compounds in water, some ionic substances in water, like NaCl, they completely ionize. So NaCl dissolves in water, you get all these individual sodium ions where the plus charge is interacting with the oxygen, that's the negative charge group of oxygen, we'll see why in chapter 8. You also have the negative charge being surrounded by the hydrogens of water. So you end up with these individual ions. So if you imagine dissolving a mole of NaCl in water, you would have 6.022 times 10 to the 23 separated ions, each individually surrounded by their own little water sphere. Now in the case of methanol, some of the waters may cluster together, they may interact together, but not really to the point where you might think of it as just being an ordinary methanol molecule intermixed with ordinary water molecules. So methanol in water doesn't ionize at all, it just exists as an aqueous dissolved molecule in the water, so it just exists as its own particle in water, whereas NaCl in water is really Na plus ions, each surrounded by water. We might write Na plus AQ, or it's chloride ions, each surrounded by water, Cl minus AQ. So NaCl, we could also say NaCl AQ, and we're just understanding that it's really completely ionized in water. So ionic compounds will completely dissolve, so this solid will completely dissolve in water, so it fully dissociates into water. So now we'll look at ionic compounds and we'll find that not all ionic compounds do this. So some ionic compounds just are insoluble in water. One example is PbI2. You're doing a lab with it in the lab, where this is insoluble in water. It just forms a solid. It doesn't ionize at all. It doesn't really mix at all with water, so it just forms a solid in water, or exists as a precipitate in water. But then the compounds like NaCl dissolve readily in water, but not necessarily infinitely. So most solids, in fact, all these solids that we're talking about here will have a range of solubility, and we're going to try to just generally come up with a set of rules that establish and help us figure out which compounds generally are soluble in water and which compounds generally are best thought of as being insoluble in water. Turns out solubility is really a range, so you can really look at all the things we're going to call insoluble and find that there's a tiny fraction of a compound you can actually get to dissolve in water, but we'll identify some as so low that practically we'll just say that they're insoluble in water. Okay, so an electrolytic solution conducts electricity. So if you just have water, it doesn't really conduct electricity very well. A non-electrolytic solution like methanol in water or sugar in water, just put any most molecular compounds are not going to ionize in water. So if the compound that you dissolve in water, like sugar or methanol, if it doesn't ionize, then we're going to have a non-electrolytic solution. And if it does ionize, like if you pour NaCl, like table salt, into water, it ionizes as it starts to dissolve, then we end up lighting the light bulb up and we have an electrolytic solution. So the electrodes can now unite because it's passing electrons to like the sodium and the chlorine ions, and they're making their way across the electrode. There's no ions in the solution to do that in pure water or sucrose, so we would say those are non-electrolytic solutions. Now, I do like to say that just because water is not a good conductor of electricity doesn't mean you should expect to be able to throw electronics into water, because that will still kill you, so don't do that. So don't think that water's conductivity is purely zero here. It's just not enough to light the light bulb up across the electrodes that are dissolved in the solution. So you notice these electrodes here just, let me use a different color, that these electrodes here just need to be connected somehow. If we could connect them with a wire or with ions, then the light can light up. So a strong electrolyte is a solute that fully dissociates in water. So a solute that fully dissociates in water, some examples here would be a water-soluble ionic compound. In fact, it would be all water-soluble ionic compounds. Now, not all ionic compounds, though, are water-soluble, so we'll have to establish which ones are water-soluble versus insoluble. A weak electrolyte is a substance that partially dissociates in water. These are going to be things that we call weak acids and bases. We'll discuss some of those examples later. One example is actually vinegar. So acetic acid is actually a pretty good example of a substance that's a weak acid. So we'll go through later which acids are strong versus weak in terms of their behavior of dissociation. Because another strong electrolyte will also be the strong acids. So strong acids we'll see completely ionized as well as all water-soluble ionic compounds. Now most other compounds are either insoluble in that they just don't dissolve at all in water, or they're just non-electrolytes in that they do dissolve in water, they do mix with water, but they just simply don't ionize in the process. And so this would be like methanol is a compound that will mix with water but doesn't ionize. And then an insoluble compound in water might be something like, like octane. Take a big hydrocarbon, doesn't mix very well with water, doesn't ionize, of course, either. It can't possibly ionize in water if it's not even in water at all. And of course, another example would be an insoluble ionic compound. So ionic compound that's insoluble in water, or maybe some big hydrocarbons would be insoluble and hence not dissolve at all in the water. So now we can predict solubility trends based on the ions that compounds contain. So if a compound contains nitrate or acetate ion, regardless of what metal it's paired up with, then we know the compound's going to be water soluble. So this chart here is showing us a list of the soluble ionic compounds. They contain nitrate, acetate ions. They also, I don't know why the book doesn't throw this in here, but also if you have NH4+, so the ammonium cation or the alkali cations, then without exception, those can pair up with anything and make a water-soluble compound. So there's no exceptions for any of these particular examples. So if I tell you you have KNO2, that's water-soluble. If I tell you you have calcium nitrate, of course that's water-soluble. Nothing's insoluble that contains an alkali cation, so lithium, sodium, potassium, rubidium, cesium. I think I said potassium, but yeah, so your alkali cations, NH4+, nitrate, and acetate, all those examples, water soluble, no matter what other ion they're mixed up with. And then chloride, bromide, iodide, generally soluble with 3 exceptions though being silver and lead. Those are the only 2 common ions of silver or lead. But mercury forms that weird Hg2, that's mercury 1. So mercury 1 mixed with chloride, bromide, iodide is insoluble. But now mercury also forms an ordinary 2+, that is not an exception. So if we give you, say, Hg2Cl2, so this is Hg2 with a 2+, so there's 2 of these mercuries, that's why I call it mercury 1. And then each of these chlorides is an ordinary minus chloride, so we have a total +2, we have a total of -2, because the whole Hg2 group has a 2+ charge. And so then our charges are balanced. This compound is insoluble in water. But if I give you instead an example of, say, HgBr2, this is just ordinary bromide, 2 of them, ordinary +2 mercury 2 bromide. This is soluble. So you can go through. There's 3 exceptions for each of these ions, so you're going to have a total of 9 insoluble compounds. So the mercury 2 compounds, completely water soluble, not one of the insoluble exceptions. And then we look at sulfate ion. The way our textbook lists these is strontium, barium, mercury 1, and lead ion are the exceptions. Other books may list different ions. Some textbooks list calcium as being an exception for sulfate. The interpretation here would be calcium sulfate is probably right on the edge of something that's kind of soluble but not very soluble. So some of these compounds aren't particularly soluble. Some books also list silver as being an exception, but not our book. So we would say Ag2SO4, not an exception, so it's soluble. We would say BaSO4, barium sulfate, is an exception, so it's insoluble in water. So the insoluble compounds don't mix with water, hence they don't ionize. All of the water-soluble ionic compounds, as soon as they mix in water and they dissolve, they completely ionize through the process. So if you have KNO2 in water, then you have K plus ions and NO2 minus anions in that solution. So think of the anions you know how to name. You're going to get those ions forming in solution, each separated by a sphere of water molecules. So KNO2 in water, you might say K plus, AQ, NO2 minus, AQ as well. So this chart here is showing us a list of the general insoluble compounds and the ions they tend to contain. So compounds containing sulfide and hydroxide are both generally insoluble in water. So let's actually look here and here. I don't know why the textbook separates these two, because look at their exceptions. So compounds containing sulfide and hydroxide are generally insoluble except for compounds of ammonia and the alkali metal cations, but we already knew everything containing those cations are water soluble anyways. But then they add 3 exceptions: calcium, strontium, and barium. Now these important exceptions are soluble. Okay, so we have to remember that if you have like copper sulfide, that's insoluble. But that if you have something like calcium hydroxide, CaOH2, that this is soluble. So the exceptions here are soluble, the non-exceptions are insoluble. Okay, and so then if we look at carbonate and phosphate, that their only exceptions are the things we already knew were soluble. So compounds of ammonia and the alkali metal cations. Now, I don't know why they don't extend to other anions as well as carbonate and phosphate, but I think if you look at other ions, the exceptions, you start to have some random exceptions and not just like a neat group like carbonate and phosphate have here. So calcium carbonate is insoluble because that's not one of the listed exceptions, but K2CO3, an exception, would be soluble, just like anything containing potassium or ammonium or nitrate or acetate would be water soluble. So identify the compounds as soluble or insoluble in water. You go and hit pause, give it a try. You might see if you can figure these out with or without the chart. Okay, let's review. So we got potassium and nitrate, definitely water soluble. So potassiums, all compounds containing potassium are soluble. All compounds containing nitrate ion are soluble in the case of the ionic compounds. Calcium carbonate, we already saw this example, is actually not soluble. This is insoluble. Calcium is not a listed exception of carbonate, so this is an insoluble compound. Cesium is an alkali cation, so cesium really paired up with any anion should be soluble, and it definitely is in the case of hydroxide. One of the listed exceptions for hydroxide is the alkali cations, so that would be lithium, sodium, potassium, rubidium, and cesium. So this would be water soluble. Silver sulfate would be soluble as well. Okay, now solubility doesn't mean like infinitely soluble. It just means that according to our textbook, I think it's about 0.1 mole of the compound will dissolve in about a liter of water, is sort of what the meaning of soluble means. So soluble just means the solubility is greater than or equal to about this quantity here. And so if you look at the compounds that we're calling insoluble, they just have a solubility below 0.1 mole per liter. So like if you look at lead iodide, PbI2, that's actually a fair bit of solubility of something like lead chloride or lead iodide. If you just look at 0.1 mole per liter, that could still be like a, in the gram quantities in terms of a liter of water. So even the things we're calling insoluble do have some relatively small solubility, but low enough that we'll just call these compounds insoluble and treat them as if none of them dissolve in water, even though probably at least some quantity of those compounds do indeed dissolve in water. Now that topic of water solubility comes back up in chapter 17 later, where you can more mathematically treat this using the ideas of equilibrium once you pick up those topics in like chapters 15 and 16. Precipitation reactions occur when solutions are mixed, generally with soluble salts beginning, so you mix 2 water-soluble compounds, and then all of a sudden you're forming a solid. One key case, if you take Ki, that's water soluble, and mix that with lead nitrate, that's water soluble as well. Mix these together and you form PbI2, which is the yellow solid, and KNO3, which remains dissolved in solution. Okay, so this question here is asking us to consider which solute particle or particles exist in an aqueous solution when each of the below compounds is dissolved in water. So you might want to go ahead, hit pause, and think about this one for a little bit. Okay, if we put KNO3 in water, it's an ionic compound, so it completely dissolves in water to form potassium ions and nitrate ions. So this is going to be 100% potassium ions and nitrate ions, each individually surrounded by a sphere of water molecules. So no KNO3 actually exists in solution. So if I tell you you have a solution that contains KNO3, you really know that it contains K+ ions and nitrate ions. Likewise, nitric acid is one of the 7 strong acids, and it completely dissociates in water to form H plus ions, each surrounded by water, and NO3 minus ions, each surrounded by water. So you get complete ionization in the case of water-soluble ionic compounds, and also in the case of the strong acids. And I just mentioned, I haven't actually listed the 7 strong acids, but there's only 7 strong acids. Sometimes it's called the 7 inorganic strong acids. There are some organic strong acids that we don't talk about in this particular class, but so the inorganic acids would be HCl, Br, and I. So HCl, HBr, HI. Notice it doesn't include HF. And then the other ones would be HNO3, and then with chlorine, so HClO3. So chloric acid in addition to nitric acid, so HClO3. Then HClO4, and then that first H plus from H2SO4. So these are the 7 strong acids. So then HF is only going to partially dissociate. I can use an equilibrium arrow. That might be the best way to signify this. I get some dissociation to H plus and F minus, but just not total. So I'm going to be remaining with some HF molecule, some H plus, and some F minus ions. So the particles in solution for KNO3 and HNO3 are the cation and nitrate ion. And for HF, my particles here would be HF, and then some H plus, and then some F minus. There's really going to be less of these ions than the molecule, so we're going to have like maybe a tiny fraction of the HF. If you imagine having 100 HF molecules, probably like 2 or 3 of them on average at any given moment are dissociated into H plus and F minus ions. Now, a molecule like methanol, this is a non-electrolyte. Now, the way we could know that is that, or let's like sort of summarize what would be an electrolyte. So an electrolyte would be, the strong ones are water-soluble ionic compounds, or 7 strong acids in water, and then the other ones would be the weak acids in water. So, and then you could say, well, what is our list of weak acids? It would be like all the other acids that we know how to name as acids. So anything that's not sort of one of the 7 strong acids that we know how to name as an acid would be a weak acid. So like H3PO4, H2SO3, like HF, the example we just saw, acetic acid. These are examples of things that are going to partially dissociate and be weak electrolytes, and then everything else, almost everything else is going to be a non-electrolyte. We'll discuss a little bit about bases. So NH3 is going to be a weak base. We'll talk about that a little bit later. This will weakly or partially ionize or partially lead water to ionize. We'll describe that a little bit later. So if it's not NH3, it's not a weak acid, it's not an ionic compound, it's not a strong acid, then it must be a non-electrolyte. And so then CH3OH would be a non-electrolyte in water, would just exist as the ethanol particle or the methanol particle in water. And then acetic acid is this molecule here, so we have some acetate ion, and then H plus, and then these H's remain intact on the acetate ion. So we get acetate plus H plus. Okay, and so then if you said, what about something insoluble? Well, an insoluble thing isn't really even capable for this discussion because it's not dissolved in solution, so we don't end up with any solute particles when something's insoluble. So if something's insoluble, it's not in the solution, so it doesn't actually form an aqueous solution, so something like lead iodide or anything insoluble doesn't really qualify for the discussion we're having here. So bases are substances that react with or accept H plus ions. They increase the concentration of hydroxide in water. And so a key example of a base might be something like sodium hydroxide, which is a water-soluble ionic compound. So it would make completely Na ions, so sodium ions and hydroxide ions. So anything that's making hydroxide is kind of the opposite of H plus because they pair together to make water. And so anything that makes OH minus in water would be termed a base. So we might look at sodium hydroxide and say, okay, that's a base. It makes 1 OH minus at least per 1 NaOH. So we'd call that a strong base because it completely ionizes to make this hydroxide ion. And then there are some substances that don't actually contain hydroxide that still make hydroxide ion. This might be like NH3. So NH3, this is a, not my writing. Let me try to erase. I don't think I can. Like this arrow is totally the wrong way. You should actually draw this. You actually draw this way. That this charge on nitrogen goes after the hydrogen and then leaves behind the charge on the hydroxide ion. This is how this would be more sketched in OChem. So NH3 goes after the H+, leaves behind the hydroxide ion. So it ionizes water, makes ammonium cation. So ammonia, we can look at this and say that this is a base. It's only a partial reaction, doesn't go to 100% completion, so it's a weak base. And then technically anything that looks like it, though we don't use these examples too often in Gen Chem, but if you take like CH3 groups and put 3 of them instead of hydrogens, then this would also be a weak base. But we don't get too crazy with these examples in Gen Chem. You might see some more examples of these things called amines in OChem. So a summary of our electrolytic behavior. So this table here is considering the electrolytic behavior among common soluble ionic compounds and molecular compounds. So this table is assuming that all these compounds we're considering are soluble. So if the ionic compound is water soluble, then it's a strong electrolyte. So there's no examples of non or weak electrolyte ionic compounds that are soluble in water. So if the IC is soluble in water, then it completely ionizes in water and is termed a strong electrolyte. If you go to something like magnesium hydroxide in water, it's technically insoluble, so it's not considered a strong electrolyte, weak electrolyte, or non-electrolyte. It's just simply insoluble, not considered to be in the solution. Molecular compounds. Okay, so our molecular compounds that are water soluble, the strong acids are in water, they completely ionize. The weak acids and weak bases, so things like HF and NH3, molecular compounds, if they dissolve in water, they would be weak electrolytes, weak acids, weak bases. And then all the other compounds that are water soluble, that are molecular, that are in water, would be non-electrolytes. So this would be something like methanol, this would be like glucose, sucrose, etc. Okay, now you might look at this chart and say, well, where are the strong bases? Well, they're already included up here. So this includes the strong bases. Strong bases are water-soluble ionic compounds that contain hydroxide ion. So they're already considered up above. So the strong electrolyte ICs also include the strong bases. So again, an electrolyte is a substance that dissociates into ions when it's dissolved in water. A non-electrolyte may dissolve in water, just simply doesn't dissociate into ions during that process. So moving on, section 4.4 is on oxidation reduction reactions. We mentioned earlier that the loss of electrons is oxidation, the gain of electrons is reduction. So if you have calcium, now our metal has all the calcium atoms in calcium solid would be uncharged. Likewise, all the atoms in O2 would be uncharged. So if we're making the ionic compound, all of a sudden these atoms have a charge. Calcium has lost 2 electrons per Ca atom. And then the oxygen atoms per atom have picked up 2 electrons per atom. So we have an oxidation reduction reaction occurring. So we have electrons flowing from the calcium to the oxygen. So the calcium is undergoing reduction, the calcium is undergoing oxidation. The oxygen is undergoing the reduction. So the calcium is losing electrons. So losing electrons is oxidation. The oxygen is gaining electrons, and gaining electrons is reduction. And so we can also look at calcium and O2 as the substance and say O2 is actually our oxidizing agent because it's the facilitator of the oxidation, and calcium is actually the reducing agent. Most agents aren't the thing. If you think of an agent for like a movie star, the agent themselves is not the movie star. They just facilitate something else to become the star, if you will. And so if you look at the reducing agent, it is itself not reduced, but it facilitates the reduction of something else. So the reducing agent allows some other atom to become reduced. So calcium is the reducing agent, it's actually oxidized. So a good property of a reducing agent is that it's actually oxidized or easy to oxidize. And a good property of an oxidizing agent is that it's easy to reduce. So O2 is, in this example, an oxidizing agent because it allows another element to become reduced in the process. And these are tandem, so whenever you have an oxidizing agent and a reducing agent present, they will exchange their electrons and accomplish one of these redox reactions. So these two reactions have to occur with each other. Oxidation, you can't just have electrons flow off into space. They're going to be absorbed by something if one of these types of reactions is occurring. So we use oxidation numbers to try to track when these types of reactions are occurring. And so it's a bookkeeping system. Doesn't always mean the atoms have these particular charges. When we think of ionic compounds, the atoms really do have the charges. So when we think ionic compounds, they really do kind of have these charges that we indicate. But when I look at a molecular compound, I have a rule that says the oxidation number of hydrogen is +1 in molecular compounds. So I have a +4 and I get a -4. It doesn't mean that the atoms actually have these particular charges in a molecule of CH4. It's just more of a bookkeeping system that allows us to establish where the charge is more residing on a particular molecule. So then if I look at something like H2O, O has a -2 charge, that's going to be its normal rule. Hydrogen has a normal rule, +1 in molecular compounds. So this is the oxidation numbers in water. If I look at CaH2, this is actually calcium hydride, so calcium 2+, ordinary state. So I have a total of a -2 for the 2 hydrogen ions, so it's just a simple H- ion. So it's just hydrogen with 2 electrons is H-. H with 1 electron is just a neutral H atom. H with no electrons is H+. And so H with 2 electrons is just simply the hydride, simple atomic ion. And so CaH2, those are the oxidation numbers of the atoms in that particular compound. So there's some basic rules here. These are going to be best exemplified through just looking at some examples. But atomic ions, they always just have whatever their charge actually is that we know already. Oxygen's charge usually -2, except for peroxides and superoxides and compounds with fluorine. Fluorine always has an oxidation number of -1. Other halogens usually -1, but when they're combined with oxygen or fluorine, then O and fluorine keep their ordinary charges of -2 and -1 respectively. Now hydrogen, its rule, +1 with molecular compounds, so when paired up with nonmetal elements, and -1 in the case of ionic compounds. But like we already saw, that's because with ionic compounds, it's actually picking up the charge that the atom of calcium is, if you will, giving up, and then in the case of water, it's more of a bookkeeping system for the charges, and it doesn't really mean that H and the O have those particular charges. And then the other atoms, if you have other atoms present, you can usually determine them by simple deduction. So let's look at some examples. It's like H2O2. It's like, just looking here in this case, hydrogen's rule +1. This is hydrogen peroxide, so this is one of those exceptions for oxygen. If I have a total of +2 for the 2 hydrogens, then the oxygen's oxidation number is -1 per each O. So I have a total of a -2 for the whole O2 group. Well, O2 with the 2-, that's peroxide, so that's why this compound is known as hydrogen peroxide. But the oxidation number of the H and the O end up being the same, +1 and -1. Okay, now for OF2, maybe I'll just do a few and alternate here because I need a little more room. OF2, this is the case where fluorine, you might remember it's more electronegative, but the rule is that F is always -1, and it never goes positive in compounds. So that means I have a -2 for the 2F, so I have a +2 for the O. Fluorine's more electronegative. It wants electrons more than oxygen does, so it's going to keep the minus charge, and then oxygen's going to go positive. Again, bookkeeping system, that this doesn't really mean that you have an O2+ cation and 2F- ions. You really have something that looks like this in terms of the Lewis structure. We'll teach more about Lewis structures later, but you really just have this in terms of the structure, and you're just picking up, okay, that the negative charge is going to reside on the fluorine atoms, and a positive charge is going to reside more likely on the oxygen atom. Calcium hydride, did this one already, -1 for the H's, +2 for the calcium, both by rules. We get those oxidation numbers. The sum of the oxidation numbers should still go to the, if we account for all the atoms, should still go to the charge on the molecule. So if I do +2 -1 times 2, that equals 0. Calcium hydride doesn't have a charge, so that should add up. Calcium's a 2+, meaning the whole O2 here is a -2. So the oxidation number per O is -1. So an oxidation number is like a per atom consideration. You're kind of considering the oxidation number of each particular atom in the compound or ion. So in this case here I have ClO3, and this is a minus charge. So I know oxygen's rule, it's -2 except for peroxides, superoxides, and compounds with F. Neither of those cases here. I have a total of -6 coming from the oxygens. I got to go to -1 here though. So that means chlorine's charge should be, or oxidation number should be +5. +5 minus 6 gives us that overall charge of -1 for this ion. So +5 for chlorine, -2 for oxygen. The oxidation number of elements is 0, so Fe is just 0. Titanium, this is an ordinary oxide because these peroxides and superoxides are only forming with alkali metals, and we also see with hydrogen, but not with transition metals. So this is just titanium +4 oxide, so titanium 4 oxide. This is a K plus, and then hence a whole O2 minus. O2 with a minus charge is the name of superoxide, and so the charge of the oxidation number in each O on average is half, so it's -1/2 for the oxidation number of O. One of the rare cases where we end up with a fractional oxidation number. Br2, elemental form of bromine, neither atom can have a charge, so that goes as 0. ClF3, just remember the fluorines keep their minus charge, they go -3, chlorine goes positive, the +3 to balance it out. And then the last one, we got potassium, we know that's a +1, oxygen is a -2, so I got a -14 and a +2 for the potassiums, so I got to have a +12 for the chromiums. I got 2 of them, so that's a +6 for each. So the oxidation number of chromium in this compound is actually potassium dichromate is its name, but the oxidation number of chromium would be +6. Okay, now I don't expect you to remember all the rules just from this example, but seeing the examples and going through how we figure these out and seeing this a few more times I think will be pretty helpful. So our activity series is showing us the relative reactivity trends of the different metals. Our alkalis are more reactive, so these elements at the top of the chart are more likely to undergo the oxidation reaction and exist in their positively charged states. The elements at the bottom of the chart are actually more stable in their elemental forms. So if you were to have a solution of, say, gold 3+ in the presence of something like lithium, it's probably going to be pretty crazy how fast these react together, because what's going to happen is gold's going to rip that extra valence electron off of lithium, and it's going to form back to the gold solid as we make lithium plus as a cation. Okay, so let's say we have gold 3+, so let's say it's AuCl3 is what we have. So that's gold 3+, and then we're going to form lithium chloride, Li plus Cl minus, so I'm going to form 3 of these compounds here and need 3 to balance out. So not a big detail in terms of balancing, but I'm more or less trying to think through that gold's going to want to reform because that's a stable metal. That's why we make coins out of it. Lithium's not a very stable metal at all. We're not going to make coins out of lithium or sodium or barium or calcium anytime soon, because if we did and they hit water or some other substances, they're going to more readily dissolve or react to form their positively charged cations. So we can use the reactivity or this activity series to help us predict when reactions will and will not take place. Like imagine I did the opposite. Imagine I took a piece of gold and I dropped it into a solution of lithium chloride. Turns out nothing will happen. So no reaction takes place because gold's reactivity is well below that of lithium's reactivity. So I don't expect you to be able to solve every problem with an activity series at this point, but we can use the activity series to help address what types of reactions may or may not take place, should they occur or not occur. They help us predict when the reactions occur and what their products might be. One of the last topics in the chapter deals with the concentration unit of molarity and then some concentration problems. And so molarity is just moles of solute divided by volume of solution. So if I have, let's say, methanol in water, let's say if I have 1.0 molar solution of methanol in water. What that would mean is I have 1.0 moles of methanol present per liter of that solution. Okay, now if I have a liter of solution, you may think, okay, how much of it's water, how much is methanol? It turns out when you start mixing solutions, you can change the volume of the two liquids. So we do try to treat the volume of the solution here and not the volume of any one of the particular liquids that might be being mixed in the particular problem. This also is a useful unit because I could take a molarity and multiply it by however much volume of the solution I use and calculate something about the solute. So let's say I'm asked, what is the concentration or molarity of 0.250 moles of sodium hydroxide dissolved in 200.0 milliliters of total solution? So the molarity, usually expressed in moles of solute, in this case sodium hydroxide, dissolved in the volume of solution but in liters. So usually we go to liters, so we can use that capital M unit, because the capital M is moles per liter. So M equals moles per liter. And so that's why we convert this over to liters. I do this arithmetic, and I get, so that calculator doesn't work. If I take 0.25, divide by 0.2, I get 1.25 moles of sodium hydroxide per liter of that solution. And that would be equal to 1.25, just capital M. So then we could do a problem, like let's say we take 37.5 mils of this 1.25 molar sodium hydroxide. How many moles of sodium hydroxide are present within that solution? Well, I can write number of moles of sodium hydroxide that we're looking for would be equal to the 1.25 moles of sodium hydroxide per liter of that solution. Then I want to multiply by the liters of the solution that I'm considering here. So 0.0375 liters of that solution. And this is going to very easily, within a very easy calculation, be able to tell me how many moles that I have present. So 0.0375 times 1.25 would be 0.0469 moles of sodium hydroxide are present within that particular solution. Now, truly there's actually no sodium hydroxide in the solution, if you're thinking about this. It's really all NaOH and OH minus ions in the solution. So I really have 0.0469 moles of sodium ions, each individually surrounded by water, and 0.0469 moles of hydroxide ions. So I can apply a little thought and try to think about what actual ions or how this substance exists within that particular solution. So dilution is a step of lowering the concentration by adding water. So imagine you take 25 mils of a 1.00 molar stock solution. So you use a pipette very carefully and precisely add 25 mils to a volumetric flask. So this volumetric flask has a mark on it, and we can fill to that mark very carefully and know that at that point the solution volume is whatever the volume is in the flask. So if it's a 250 mil flask, and I know at that point I have about 250.0 milliliters of total solution volume in the solution. So if I take 25 milliliters of my stock solution, add it to a new flask, and then fill the rest of the volume up with just pure water, what I'm doing is diluting the solution. And the way I'm diluting it is I'm taking the moles in the blue color, that's probably some sort of copper solution, and I'm lowering the concentration just by adding pure water. So there's an expression we'll use a lot, M1V1 equals M2V2. This works because this is a molarity times a volume. We see that gives us moles. So this tells us our moles before the reaction, or before the dilution, and that if we're just simply diluting, we're not really changing the number of moles of the solute. So the moles of the solute are not changing by adding water, and so that puts our M1V1, our initial molarity times our initial volume, equal to our final molarity times our final volume. So if I have 25 milliliters of 1.0 molar solution, and I'm diluting it to a new molarity, but to 250 total milliliters, then the new molarity, our M2, would be just now equal to 0.10 molar. So I've just effectively reduced the concentration. Actually, I need one more sig fig if you're tracking. So 1.00 molar is my new concentration. Okay, now this particular problem of like an M1V1 equals M2V2, this type of solution works whenever we have a dilution problem. You might see some problems later called like titration problems, and those are going to require a different type of solution, or a different type of a way to address solving those particular problems. And we'll talk about that method when we get to those types of problems. But just know, if you have a chemical reaction taking place where you're adding two solutions that are mixing together and reacting, maybe each solution has a molarity and a volume, that in those types of problems, we have to think of a reaction and stoichiometry and solve some sort of problem like we did in chapter 3. But if we're just simply adding water, then we might be using this dilution equation. So one of the final topics in the chapter deals with solution stoichiometry. We know you can use a molar mass to take a mass of substance A and convert that to moles of A. Like you can use a molar mass to go between moles and grams very easily. Well, it turns out you can use molarity and volume to go back and forth between moles as well. So you can use molarity and volume and moles and go back and forth between these units as well, just like we can go back and forth between a molar mass, grams, and moles like we did in chapter 3. And so if you imagine we have some sort of reaction, A plus B goes to C, you can imagine maybe A is a solid, and so maybe you have a molar mass of the substance, and you can think of how much mass you're adding. Maybe B is in solution, so maybe you have a molarity of B, say it's 1.25 molar. That's what the M means, so moles per liter, and you have a volume of it that you're being told, so you can figure out how much of A and B need to react together, solving a stoichiometry problem. So one such problem we might look at here would be how much sodium hydroxide is required to fully neutralize this quantity of phosphoric acid. Now, what we mean by fully neutralize is that we're going to take H3PO4 all the way down to the original ion we know how to name of phosphate. So we're going to go all the way to Na3PO4 as our product. And then what we're doing at the same time as we're sort of doing the switching of plus and minuses, if you will, is that we're making waters. So we're going to take 3 NaOHs to get our Na3PO4s, and I'm going to form 3 H2O molecules. So I make 3 water molecules, and I make this aqueous. We know it's aqueous because it contains sodium ion. So I end up making Na3PO4 AQ in this process. So this is my basic reaction here that I can write out. We'll get a little bit more into predicting reactions later. We haven't talked too much in this video about this, but imagine we know this base and this acid react together to form this salt and this water. And so what we can do is how much of 0.1 molar sodium hydroxide is required to fully neutralize this given quantity of 125 mils of H3PO4. We can make a BCA chart. I'm going to use a dimensional analysis step. So how much milliliters of the NaOH solution is needed, that's what we're looking for, is required to fully react with all this H3PO4. So I got 0.100 moles of H3PO4. Write that out every time. This is really helpful because these problems aren't hard as long as we keep our units straight. And sometimes we just have to think M, that just means moles of this per liter of that solution. So then I can multiply by 0.125 liters of that solution. That tells me the moles of H3PO4 that are present. For every 1 mole of H3PO4 that is present, we need to add 3 moles of sodium hydroxide to react with it. And then we're told that we're using a solution that has a concentration that's 0.100 moles of sodium hydroxide per liter of that solution, and then a liter is 1,000 milliliters. I could add another step or just cancel out the liter for 1,000 milliliters rate in a single step. So go 0.1 times 0.125 times 3. So I need 0.0375 moles of sodium hydroxide. I'm getting 0.1 moles per liter times 1,000. That's 375 milliliters of the sodium hydroxide solution is required to react with this acid. Now, we'll discuss titrations later, but a titration is basically going to be if I have this acid and I'm adding the base to it dropwise, I can have an indicator present that might be one color. Let's say that that color is clear. So the acid color, let's say in the base or in the indicator we're using is clear, and I'm adding this base, and you might see these like colors form and then they dissipate quickly. And then as soon as you see a pink color persist, then you know you've added just a tiny bit of excess sodium hydroxide. So you can do some problems called titration problems that allow you to work out unknown concentrations. We'll talk about that particular problem later, but I just wanted to allude to that here at the end of this video. So hopefully this gives you a good idea of what's to come in Chapter 4. We're going to do a lot in Chapter 4. We're going to do it pretty quickly, so hopefully this gives you a good start. So I'll see you guys in class. Thanks for your attention.